So, you know, a few of our meetups, a bunch of people express interest in time series databases. Seems to be a very hot topic at the moment, and you know, it's kind of which ones to use, all that kind of stuff. We've got a lot of experience in this area, so I thought I'd share our experience, our story of how we actually built our own one to build our monitoring service Outlyer, and pretty much advise people not to do it if they can avoid it. So. Essentially, just a bit about us. I kind of mentioned at the beginning, we're a monitoring company, so obviously we collect metrics, we monitor Kubernetes and cloud and thousands of servers with big customers like Netflix. And essentially, because of that, we need a time series backend to collect all those metrics. And one of the first attempts to talk about it a bit, we actually were all contributors to a open source time series database called DalmatinerDB, built in Erlang. I'll talk a bit about that in a minute. But some of you may have heard of it. It's an open source time series database, so we pretty much inherited it and pretty much took it over. We also have, I think, the top blog right now for all the listings of all the time series databases out there. So if you search for top time series databases open source, you'll find that blog. And so you'll find a whole list of every single time series database you can imagine, with every single feature and all that kind of stuff like on there. Of course, we organise a meetup, so that's kind of our experience with time series databases. We built one, we've kind of evaluated all of them, and we need one for our own service. So we know a lot about the space. And so kind of just the context at a high level, as a monitoring company, how we work. So we have agents that get deployed out to different environments. They send data back to our exchange, they get put in a queue, and then we put them into time series databases. Obviously a bit more complicated than that in real life, but that's kind of a high level kind of architecture. So with our first version, this is back in 2013 when we took kind of the very first version of Outlyer. You know, the core requirements for any kind of time series database is essentially, it has to scale. Everyone wants infinite scalability on these things, high availability, and it has to perform, so people can load up their graphs and their dashboards really, really quick. So we kind of started that, and so the very first version I actually built was just based on Riak. So do people here know Riak? Hands up if you've used Riak or know what it is. Right. Yeah, cool. So Riak, what we liked about it is very operationally resilient. You can kind of destroy nodes, put them back in, it just clusters, rebalances everything. It's very durable. So we started with Riak, and it's basically just a key value store, and we put all our kind of metrics into that. It worked pretty well until we hit our first file. When we first started onboarding, we got paying customers pretty much from day one. It's an ambition of mine to sell Outlyer before it was a product. And so pretty much from day one, we kind of got some customers on board very early on. And once we onboarded like a really big customer back in the UK, we started hitting files. So they were starting to see some performance issues and stuff like that, and they started putting on, I think, over about 1,000 servers at the time. And so that was really our first file. So we did what every good DevOps team does, and we solved it with caching. So we basically put Redis in front of it, and that actually worked really well for a while. But when we kind of took a step back and looked at, what do we actually want to do? Like what does the monitoring tool need in the new world that was evolving of containers and Kubernetes? This is back a while back before that stuff was really popular. We realized that we're going to have dimensional data. So that means, not just sending metrics in with just a name, but also being able to put labels on those metrics, so you can say this metric's coming from this region or this server or this kind of thing. And we're going to have we need to have more advanced analytics than we can provide with something simple as Riak, which is really just a key value store. So we at the time couldn't really do really advanced analytics. So when we kind of took a step back from that, we decided we'd have to kind of basically build something that could actually do all that stuff, and we couldn't do it on Riak. So we had a kind of choice. It was either we build it kind of custom, completely from the ground up, probably on top of Riak at the time, because that's what our experience was on. Or we buy it, so we just buy or take something from the open source community. And this is back in 2015, so some of the offerings out there weren't as mature, like PostgreSQL and things like that. Or you inherit. And the reason I say inherit is eventually what happened is we went out there, we looked at all the time series databases at the time. I think it was PostgreSQL was probably the main one. There was one year in 2015. At the time, we didn't really have clustering, and it wasn't very mature, so we didn't think it was going to scale to our needs. We were actually running a pretty big scale at this point. We had quite a few big customers. So we actually found this crazy guy called Heinz, but he kind of taken advantage, he kind of optimized it for time series data. So he uses ZFS file system on Linux to kind of compress the data so we can store it all. A lot of data at scale without using gigabytes and terabytes of data, although we ended up going to that anyway. And it was kind of right optimized for kind of storing lots of metrics coming in. In fact, you could actually do about 3 million metrics a second with our test on a single node. So I had all the clustering, so you kind of made some smart decisions about, clustering I'm going to get from Riak, compression I'm going to get from ZFS, and then I'm just going to build the kind of analytics stuff on top of it. So we kind of inherited it, and at the time it didn't really have dimensional support, so we didn't have the ability to query tags and do advanced analytics. So we kind of added it on, so we kind of built the Postgres kind of index, which kind of sat next to it. We made a lot of extensions to the query engine. Essentially, we ended up pretty much becoming the core contributors to this project. And it worked pretty well. You can see some of the graphs from our old product. Kind of there, we were rendering like 10,000 data points on a single screen, just like loading months worth of data, and it was popping up pretty fast and working pretty well. That was until containers started becoming a big thing, which also happened around the end of 2015. And one of the things about containers that makes time series really hard is series churn. So what series churn basically means is, a container, let's say each container collects like 10 standard metrics, CPU, memory, whatever, for each container. And then you switch off that container and switch on another container. So those metrics stop, then another series of metrics, created, then another and another. And we had one customer that was churning through their containers every 6 minutes on the test environment. And we're talking about 1,000 containers like just running on this test environment. So you can imagine our indexes started building pretty fast, and this was all in a single Postgres kind of database. So we kind of got a bit caught off guard with that. So eventually we ended up with this problem where it was basically infinitely growing Postgres index of all our metrics. It got to the point where we had to run cron jobs at every hour, just basically clear out all the old metrics and basically make sure that the other metrics are still easily searchable and stuff. We can build queries and all that kind of stuff, and that kind of worked for a while. But ultimately we had to basically just change the way we did indexing. And Prometheus 2 had a very similar problem as well to the previous one. Essentially, as more kind of, as you get this kind of problem of series churn, the way to solve it is you have to kind of divide your indexes up into, partition it by time, so that when you do a query, you only look at the partitions of the time range you're looking for, and you only see the metrics in that time range. So we ended up solving it very similarly. We ended up partitioning our indexes by time. So if you did a query for the last hour, you'd only see the metrics that were collected for the last hour. If you did over 2 hours, the last two indexes, the last two partitions, etc. So that actually worked really well, and actually Prometheus 2 is taking a very similar approach for solving that problem in Prometheus. But then, we grew, we had some really big customers, and we have a lot of customers that once they come in, they start with us with like 100 servers, they end up growing like 2,000 servers in 6 months, and we ended up having our third file where we ended up onboarding a mid-level SaaS company in the US, and one of their teams decided to use us pretty much for the same use case I think is like Amplitude for, which is basically all their customer mobile app kind of analytics were basically being used for us. So it wasn't really being used for containers and servers and Kubernetes and all that stuff, it was being used for actual customer event analytics. And when they switched that on, we ended up ingesting from just one team 30 million metrics. Like it just went boom, and it just kind of came onto us. And we were literally firefighting from that day forth. And we managed to keep it running, managed to keep it going. It was a very tough few months, but we ultimately had to fix this. Like we couldn't, keep going in and having to kind of firefight this. So one of the lessons we learned during that period is, we were very proud of the fact Dalmatiner could do 3 million metrics per node, and that is a fact. Like if you want to test it for yourself, you can spin up a node with Dalmatiner and it will ingest 3 million metrics a second. It's actually relatively easy to write metrics to disk because you could literally just write a program and just stream stuff to disk. And if you've got designed the right way, getting a high write volume is relatively easy. It's actually really hard to query. That's where the problem is in this time series space. And because of the way Dalmatiner works, it doesn't run the queries on each node and then send an aggregating thing. It had to send all the data back to the query node, which would then basically process it. So the processing time of 5 millions of metrics is very quick. But to send all that data over the network, we were getting some queries sending 40 gigabytes of data with just a single graph, just to pull the data for like a 6-month time period, calculating all the queries, so we learned the hard way that trying to make these things read very fast is a really hard problem. We did eventually solve it, and we solved it. The second kind of tool that most DevOps people use when they want to solve that is sharding. So we ended up having to shard all of our customers, and that did actually stop the fires and keep us going for another year. But it was clear to us at that point, we were putting a lot of resources into building a time series database. We're not a time series database company, we're a monitoring company that needs time series, but that was diverting attention away from end user features and all that kind of stuff. So we decided, if we carry down this path of having to be like the only user of this, we were probably the only main user of DalmatinerDB, being the core contributors of it, having half our engineering team pretty much building and maintaining it. We weren't going to get the investment I wanted, from my point of view as a CEO, talking to customers and stuff, of doing all the really cool stuff that we've ended up doing later on. If all our engineering team was just going into solving this problem, which wasn't really, that's one of the reasons why people buy monitoring tools at SaaS, is because they don't have to build and maintain it and everything like that. But that's not the only reason. We need to do other things as well. So it kind of got to the point around 2016, that we realized building a time series database really sucks. If we're going to have to do things slightly differently. But the good news is by that point, we'd come as a team that basically had never really done this before. We didn't work for Google and Facebook and all those kind of things, so we had to kind of learn the hard way how to build these kind of time series databases. And by this point, we're 3 years in, I think we could say we were pretty hard-nosed kind of experts now in this space. And so, I want to summarize kind of like why is time series hard, why is it hard to build a time series database, and the lessons we learned kind of doing that. So, as Choice BIG once said, he predicted microservices, more services, no problems, and basically, one of the trends that's kind of made this kind of problem with time series really hard is as you add more, as we went to cloud, as we went to containers, as we went to Kubernetes, as we went to microservices, just the number of metrics that everyone's collecting is just going up exponentially. So this problem is becoming even harder than it ever was when we got started in 2013. And obviously, as you have more metrics, you're getting more, the number of metrics that each customer is collecting. We work hard now to see the actual number of metrics that are kind of coming in. Our average customers, can easily do 2 or 3 million metrics a minute. And some of them are doing way more than that. So so the number of metrics becomes really hard, and if you're doing that across multiple customers in the multi-tenant SaaS environment, that number gets really large very quickly. And then of course I've already talked about the problem we saw in 2015, which is metric churn. So I think this graph is from our own data. I can't remember exactly what the axis is. But I think this is basically a graph that they were doing at the time with that customer that was cycling containers every 6 minutes, like how many metrics were basically getting churned, every 10 minutes or something like that. I can't remember exactly what the graph stood for. But essentially we hit the series churn problem as well, just like every other module tool out there. And containers have made the job a lot harder. And then to compound the issue, developers aren't very patient with monitoring. It's kind of like, I'm a developer, but we're kind of used to instant gratification. We're used to searching on Google and getting results in 0.25 seconds or whatever. It's the same for monitoring. Developers just want to dump all their metrics, as this customer did with the 30 million metrics, and they expect everything just to kind of snappy and fast and everything like that. And actually, Amy, she's one of the devil's team, on the observability team at Pinterest. She does a talk on like the UX monitoring tools, and one of the key tenets she has is performance, do whatever it is to make it fast, because they've noticed if their users get sluggish dashboards and sluggish graphs and stuff like that, people just stop using their monitoring system. They want to start using other things and things like that. And the problem is like the expectations now, it just has to be fast. I want to put in 10 million metrics and I want to get super fast results and stuff like that. And that is actually a really hard problem to do at scale, high availability and all that kind of stuff. So that's also another thing that's kind of changed over the last few years as well with monitoring. So, and then remember, when you're building it, you have to still have it scalable, highly available, performance, all that kind of stuff. But there are a few things that do help us when it comes to time series. So one of the things, this is another graph of some of the queries I think we just monitored for a while. Basically, most of the queries that you see on most monitoring tools have the last hour. You could actually throw away all the, you can throw everything after an hour most of the time, and most users won't even notice, because most of the people are looking at what's happening right now, what's happening in the last hour. I think we found, and we've seen other blogs from other companies talking about the same thing, over 90% of the queries were all in the last hour. So that means that the actual value of the data tells off exponentially after about 1 hour in your monitoring system. And that can help us. The other thing as well is writing type 2 database. It's not like a normal database where you can kind of go in and insert rows and update rows and all that kind of stuff. It's always coming in a constant stream, and you're just writing, and it's useful. You don't need to go back and edit a data point in the past, or whatever, especially for the operational use case of time series. So you can kind of write things and forget about them after you've written them, kind of thing. So that is actually a very helpful feature of time series. And as a result, it doesn't have to be assets. So you don't need to do transactional writes, because you don't care. Like in the operational use case, if you're collecting millions of metrics, and let's say you lose 10 data points, every now and again or something, like generally you're not even going to notice it on the graph. So you don't have to build this really complex database that basically guarantees storage of every single point and data point you're collecting, because ultimately at the end of the day, if you lose a few here and there, that's okay. The most important thing is it performs, and you keep the majority of those points kind of coming in for the end users. And that's another feature we can use to simplify this problem. And then of course, reads are defined across a defined period of time. So, and last but not least, there's actually some really handy compression stuff you can do. So, has anyone here heard of GorillaDB from Facebook? So they've done a really great paper on a compression algorithm. They've done the time series. They noticed that most data points don't change that much, between measurements. So instead, they kind of take the XOR between the data points, and so the amount of data they store per data point is actually very easily compressible. They did that in memory. We actually use in memory now as well, and we use a very similar kind of algorithm to compress it. So actually, there are some features about the data you can use to compress it quite substantially. So that brings us to kind of 2017 really, when we kind of pretty much rewrote everything from scratch, and we kind of redesigned the entire architecture, and we pretty much launched the architecture in January 2018. It's now all of our customers are on the new system, and so I'll kind of show you now where we kind of ended up and how we kind of addressed all these problems. So the main thing that we realized is all these open source tools out there, like PostgreSQL and these other things, they're built to be easy to install for an operations person. So it's a single process install. I install an RPM on my server, and that RPM includes all the processes in one kind of thing that allows me to kind of do my roll-ups, do my ingestion, do my queries, all that kind of stuff. And because an operations person doesn't want to be managing 20 microservices just to run a time series database in their infrastructure. But if a monitoring company like us, we don't care. We care about scale and performance and ease of scaling each of the different components. Roll-ups, you may want to scale independently from writes and reads and all that kind of stuff. So the first kind of major decision we made was we're going to unbundle the database. We're not going to have it all as a single kind of install that you install in the servers. We're going to basically put the application on one service, Kafka, with Kafka. We're going to use S3 for durability for like long-term storage. That's not what we read from, but that's where we do our backups and we can reread everything. We're going to use Atlas, which is around a minute for the time series in memory. Console for kind of doing all the distributions, and EC2 for scaling and all that kind of stuff. So we've now broken that single database into a bunch of services that we can independently build, manage, tune, and everything like that, instead of trying to do it all in the monolith. And one of the key components we used is, has anyone heard of Netflix Atlas? So we ended up actually adopting that. Now, as a time series database, it is awesome. It's extremely fast. Netflix uses this for all of their monitoring internally. They like to joke they're the biggest monitoring company that streams movies, so they do a lot of monitoring using Atlas. And but one of the things about Atlas that you don't realize until you use it is that a lot of stuff around the sides you have to build to use it. It's not like you just put an Atlas server up there and you can just start using it as a time series database and start collecting it. You need to build stuff to blend the queries across different tiers. You need to build stuff to kind of ingest the metrics. There's a whole load of tooling and architecture that you have to build around it because they have an open source, because each company has a different kind of architecture for that. So it's a component, not a full solution. But as a component, it's in memory. It's got a full analytics capabilities for all the different things you can think about, standard deviations, percentiles, all that kind of stuff. And most importantly, one of the things we learned the hard way is sensible limits. Like they don't let you just send millions of labels in. Most people don't. They put some kind of predefined limits on kind of what data you can send in there that essentially stops you from getting into stupid scenarios where you're trying to scale for everything. So we really like that. And the other thing as well is, because now we're starting to break it all out to different services, we could break it into multiple tiers. So, like I said, the first hour of data is the most important. So we actually store about 6 hours raw in memory, immediately available, get stored into Atlas servers that you can query instantly. So metrics come in within about 2 seconds, you can see them on a graph. So they stream in, go into the first tier. Then we basically roll up the metrics over time into different tiers, which increasingly get longer and longer, 5 minutes, an hour, that kind of stuff, for about 13 months. But the good thing about this architecture is we can tune it for each customer, so if they want 4 weeks of full retention, we can do that. But yeah, basically, so now we've broken up the tiers. So this tier is the most important one. This is the one everyone's using to query everything. These tiers are less important, but they're there if people want to do longer range queries without, for other use cases. We built sharding in from day one, so we have like a big Uber shard for all our small customers, so we can still do the $100 a month customer who's got 10 servers and all that kind of stuff. They can sign up for free. We can support that because we have a big Uber customer for them. But then for our bigger customers like Netflix and other people, we put them onto independent shards. That means we can independently tune their environment, we can independently scale them, and we're not going to end up in a situation where we had previously where one big customer can just come and dump in 30 million metrics and all our customers are affected, not just us, kind of thing. So sharding's kind of been built in from day one, and we use console to kind of dynamically shard everything. So pretty much console is the source of truth that when metrics come in, we use that to kind of say, oh, this is a B2C metric, we'll put it in the B2C shard, etc., etc. And yeah, there's a whole bunch of hashing and grouping built into that, which I can talk about after this if you guys are interested. That allows us to kind of make sure, because one thing about Atlas, just to kind of say, it doesn't cluster. And actually that's really good, because clustering makes databases really hard. It adds a lot of complexity, it adds a lot of network chatter. You don't really want that in a monitoring tool. So we actually have everything's independent nodes. We use N-shape mirrors, so we have 2 mirrors for each database. If one goes down, we spin it up. We can basically reload the data in about 3 minutes. Within that, we have like just a simple kind of hashing algorithm that basically means that when we write the data and when we read the data, we use this hashing algorithm to say this is gone on this mirror over here, this metric's gone on this mirror over here, and we can use that hash to basically calculate where it is and basically put it back in the right place. So that's what the grouping stuff is for. And then ultimately, because now you've got everything stored across multiple tiers and you've got the one with multiple mirrors and all that kind of stuff, you need to kind of blend the queries across all those different tiers and nodes. So we have a query engine that basically can using console knows where the data is and can basically send those queries out to all the different nodes. They're computed on the individual nodes, they send out the data, and then we blend them. And one of the things with blending across multiple tiers with different resolutions with time series, if you do a really long query for 30 knots, you're going to get 1 hour resolution. You don't need anything more than that for 30 knots because effectively you wouldn't be able to see it on the graph. So if you're putting data from the short-term tier, which is real-time resolution, and the long-term tier, we just aggregate everything up into 1 hour resolution, so you get a unified graph on your thing. That's what happens in the kind of blending tier. So when you put it all together, this is now the architecture we've ended up with, and so if you kind of blow it out, you have agents kind of pushing stuff to Kafka, and Kafka is pretty popular, Amplitude use as well. And what we do is we basically push everything to short-term storage, which is like the in-memory kind of Atlas tier. We dump everything onto S3 in real time as well, so that becomes our backup. Another thing as well about time-series databases, really hard to back up when they're running, because the data is constantly being written in and stuff like that. You can take snapshots and stuff, and once you get to a certain scale, that process starts taking quite a while. So instead of trying to back up databases, we actually just write everything in parallel to S3. That becomes a backup that we can basically replay into any of our nodes if we need to reload the data, and we can do that in about 3 minutes if the node goes down. So that's actually our backup store, and it's also our separation for the tiers, where we then can basically roll up metrics using MapReduce into different tiers and into long-term storage. And the long-term storage nodes, actually, we've got a custom parameter that uses disk-based storage, because doing it in memory would be really expensive for long-term data, especially for data that most people don't access. So that kind of works a bit differently for me and MapReduce. But yeah, that's basically the architecture we have ended up with, and it's been working really well for last year. And you know, I guess in conclusion, you know, building a time series database is getting hard, and only getting harder as the number of metrics goes up exponentially. Obviously I'm biased, but you know, if you've got the money, outsource it, because it is a really hard problem to solve. And yeah, that's pretty much it. But that's kind of our architecture and how we kind of got